Okay, in this presentation we are going to look at the Pareto distribution, the Pareto type 2 distribution, and we're going to look at mixtures of two Pareto type 2 distributions, okay? Now, this actually, at the first instance, seems very difficult, but actually it's very straightforward. In fact, it actually goes back to the fundamentals of mathematics, probability 101, okay? Conditional probabilities and laws of total probabilities and axioms of probabilities and so on. So that's the sort of level we're at actually, is with the general level of sophistication with the question and answering the question. For a property and casualty insurance company, losses follow a mixture of two Pareto type 2 distributions with equal weights. That's important, the equal weights, okay? So 50% are from type 1, or sorry, the first one, and 50% are from the second one. I'll call them A and B just to sort of not be talking about first and second, type 1 and type 2. So A, probability distribution A, is a Pareto type 1 or type 2 distribution with alpha equal 1 and theta equals 50 or 500, okay? And Pareto type 2 distribution B is very similar, except alpha is equal to 2 and theta equal to 500. And what we're asked to do is determine the value at risk at the security level of 95% for the entire portfolio. Okay? So 50% are from A, 50% are from B. They have different sort of shapes essentially. So anyway, so this is the value at risk formula here. Okay, for type 2. Okay, now that's not really what we're looking at actually here. So it's actually much simpler than that. Okay, so what we're really going to be working with is this formula here. Okay, the cumulative distribution function. In fact, what we're looking at is really the survival function, okay, which is 1 plus x over lambda, or here it's theta actually, I just changed it to theta because we just sort of stated theta in the question. Sorry, this is just a general formula sheet, and here the answers are written in terms of alpha, but in this case what we are working with is thetas, okay? Anyway, so that's the survival function, and it's just based on the cumulative distribution function, okay? And again, I'm using theta rather than lambda. Anyway, so what we can do here is just re-express the survival functions as follows, okay? So I just sort of skip past this because I don't want to spend too much time on showing what the survival functions are. But essentially, the survival function of x in both cases is 500. Well, it's 500 in both cases, which is theta, okay, divided by x plus 500, which is theta again, to the power of alpha. Okay, that is what our survival function will work out to be. Okay, so we have two survival functions for two distributions. In one case the alpha value is 1, and in the other case the alpha value is 2. Okay, so hence we have 1 here and 2 here. Alpha equals 1, alpha equals 2. In both cases theta is 500, so we don't have to worry about that. Okay, theta there. Okay, now, okay, I just paused for a second there just to catch my breath. Okay, so this is where the law of total probability comes into play here. Okay, so here we have portfolio A, and over here we have portfolio B. Okay, and in this case 50% are from A, okay, and 50% are from B. And of the 50% that are from A, this is the expression that will give us, there's some value x, and this will give us the proportion of the total number of claims from portfolio A that's greater than x. Okay, So this expression here is the survival function of x for A, the portfolio A, the first of the two Pareto type 2 distributions. Now, so essentially this tells us the probability of a certain proportion of the claims being greater than x, okay? So it's 0.5 times some probability, okay? And likewise, portfolio B over here, okay? This is the exact same thing, it's just that alpha is equal to 2, so this is the survival function for the second portfolio B, okay? 500 divided by x plus 500 squared, okay? Now, this is the probability of it coming from A times the probability that, given that it comes from A, that it exceeds x. Okay, so it's sort of a conditional probability in this case, okay? This is the probability that it comes from B, and this is the probability that it exceeds x, given that it comes from probability B, okay? Now, what we're asked to do is find, let that equal to, we're asked to find the VAR of 95%, okay? So that means altogether, 95% of the values should be less than this threshold x, which is to say 5% should be greater than this threshold x, okay? So this is just 1 minus p because we're dealing in terms of survival functions, so the survival function probability corresponding to a VAR of 95% is 5%, okay? If 95% are less than this value, 5% are greater than this value, okay? So the overall probability there is 5%. So what we have to do is solve for x, essentially. So we have this expression here. Essentially what I'm going to do is just ease out or cancel out the 0.5s by just multiplying the whole expression by 2. So the 0.5s disappear, and what we have over here is 0.10. Okay? Now this is an awkward looking expression. So what do you do here? Well, what we could do is just change it into a quadratic. Y plus y squared equals 0.10. Okay, so we factorize that. Okay, so let that equal to 500 divided by x plus 500 equal y, and solve for y. So this is what we got there. So just to make life easy on ourselves, just multiply everything by 10 and just turn that into a conventional quadratic equation. Then we use the good old minus b formula. So minus b plus or minus a squared, or b squared minus 4ac divided by 2a. Hopefully you should know that one off by heart, but you know, does you no harm to sort of practice it every so often. So what we should get there is, you know, you should be well past that, more than capable of that. So we get these two numbers here, okay? Those are the two factors of that quadratic equation. Now we disregard that one because we need it has to be positive essentially. We take the positive root, y equals 0.0916, okay, and then we solve for x. So that should be straightforward enough. Cross multiply, we should end up with x equal to 4,958.04. That is the answer we're looking for, okay. So what was the hard bit, so to speak? And it wasn't even that hard really. It was this. This is the law of total probability. Probability times the conditional probability plus probability times different conditional probability gives an overall probability. That's essentially all we were working with there. So this is probably just like you sort of seen in one of your very first statistics modules. That's all we're doing. I know when you're dealing with things like value at risk and mixture distributions and Pareto distributions, you're expecting something quite complicated. In this particular instance, it's not that complicated really. It's just recognizing what to do. So that's how we do it there, okay? And that's how we get our results. Obviously, you know, these things could pop up now and again, the factorizing quadratics. You know, you won't be forgiven for messing that up. I know you probably don't do that very often. You don't do calculations like this very often anymore. But that doesn't mean that you'll be forgiven for not knowing how to do it. You have to be on the ball with those sort of things. Particularly as overall, it's actually a fairly easy question. All right, that's grand. We'll leave it there.